data space which could be used by some other process. And they said that, okay, let's use best fit, maybe it will be more efficient that way. And the experiments show that best fit is not more efficient, okay? Actually, it wastes more memory than the first fit. It wastes more memory than the first fit because, I mean, you will not find exactly the same amount of memory available in the memory. So you are going to use a little bit larger than memory than what you need. And that a little bit larger than, I mean, you need 4Ks. You need 4Ks, but you found 5Ks. So 1 kilobytes of memory will not be used, right? It will not be used. And 1 kilobytes of memory will be available so for other processes to be used. But nobody wants that kind of small amount of memory. So it fragments your memory even more. So it wastes memory. It is not better than first fit, as we thought that it would be. Best fit and first fit actually, they perform almost their performance in terms of memory usage is almost the same. So some people say that instead of using best fit, let's use worst fit. What do I mean by worst fit? First fit, find the first location available and it uses it. It doesn't care if it is very large or very small, or as long as I fit in there, I would use it. Very fast to find the first position. Merging is okay. This one finds the closest fit, okay, and we say that this creates very fragmentation problems. And some people say that, okay, let's do it with the worst fit. What do I mean by worst fit? If I need 4 kilobytes of memory, worst fit, I mean, if there is a space that says 2Ks of memory is available, can I use this? No, because it is not good enough. I can't fit in there. But it says that find the largest memory location available and use that one. Okay, let's say I have 2K available, okay, 4K available, and 100K available. Okay. Okay. So maybe I should do this too. And 8K available. Let's say I need 4Ks of memory space, and these are the available spaces. First fit says that, okay, I'm picking this one. Best fit says that I am picking this one. And worst fit says that I am picking this one, the largest one. Okay. It picks the largest block and subdivides it. Okay. It takes this 100K block and takes 4K out of it. And it says that now 96K available from that chunk. Okay, from that chunk. That says because best fit tends to leave small, useless blocks. Nobody uses those small blocks because they are very, very small. Nobody needs them. It makes this fragmentation. If I use this large chunk, then whatever remaining will be used by some other process, and that will make my memory unfragmented. Okay. Again, simulation results says that the idea does not work. Okay. The idea does not work. First fit and best fits are better and pretty close, and worst fit is not better in terms of memory usage. And these are the numbers actually, very, very bad numbers. Okay, the first fit or best fit, as much as 1/3 of the memory may not be usable, because of this fragmentation issue. I need memory of, let's say, 100 kilobytes, but when I look at the memory, I can't find that 100 kilobytes of available space because it is all fragmented. Okay, it looks like this. Okay, this is my memory. Okay, it looks like, okay, this space is available. This is used by some process, and this small space is available, and some process, and some small space is available, some process, some small space is available. So if I add all these unused spaces, maybe the total is maybe 200 kilobytes. But none of them is good enough for me to find 100 kilobytes of space. So this is a fragmentation issue. So what was our solution for the fragmentation? What was the solution for the fragmentation? Last time we talked about it. Solution for the fragmentation. How do you solve this problem?
Kaydırıyor prosesi.
What was the name for that?
Hatırlamıyorum.
So you don't read the book, you don't watch them. Okay, it was called rest compaction. Okay, you compact your memory. What do I mean by compacting memory? You move these processes. Okay, you do this. Okay, let's say P1, P2, P3, P4, and you do this. P1, P2, P3, P4, okay? And now I have 200 kilobytes of available memory space here, okay? This is called compaction, okay? You compact your memory. That means that you need to relocate your processes from this memory location to these memory locations, okay? It's called compaction. Okay, but compaction was expensive, right? You need to relocate all of the stuff. Şu bilgisayarı oradan kapatır mısın ya? Onunla oynayıp durma ya. Okay, any questions? Okay, let's move on then. So, best fit, yes.
What if my process needs, my processes never needs to be grown?
Okay, we talked about it a little bit actually. I mean, we said that we are talking about the memory allocation as a problem of like a fixed size allocation. But last time we talked about it, we said that usually processes need more memory than their initial allocation. So when you are allocating memory, allocate more space, okay? Allocate more space so that there is enough space for the process to grow into. Okay, so if the process needs 4K of data, okay, 4K of memory space, then allocate maybe 6K or 8K. Put the space in like that. Okay, put the stack at the top, and the program is at the bottom, and your global variables, etc., or the heap, and in the middle of the process address space is empty. So allocate more space, and if it is not enough, and that space is not enough, then you need to relocate your process, and the operating system is responsible for relocating it. Okay, so it's a probably good idea to allocate. First, it's a good idea to read the book, okay, because this is written in the book, and I already talked about it. Second, it's a good idea to allocate a little extra memory whenever a process is swept in or moved. Okay, first fit, next fit, best fit, worst fit. Okay, so this is a very wasteful amount of wasteful space, and if I don't want to waste this space, then I need to compact my memory. Again, that's inefficiency. I need to find some other solution, and we will. I mean, unfortunately, these types of algorithms that uses swapping or the base registers, they will not be very, very efficient. Whatever you do, however you keep your memory, they will not be very, very efficient. Another algorithm for this type of memory management is the quick fit. Quick fit keeps a table with n entries. Okay, it's like the best fit. Remember, the best fit orders the linked list by size. Quick fit also kind of does the same, but it keeps more than one linked list. It says that, okay, these are my linked lists. Okay, this one uses 10 to 100 kilobytes of available memories. This one is 100 to 1000 of memory locations. Okay, and this one is from 1000 to 10K, and it goes like that. Okay, so at each linked list, you have similar sized holes. Okay, you have similar sized holes, and they are ordered by the hole size. The first entry is a pointer to the head of the list with 4 kilobyte holes, then 8 kilobytes, then 12 kilobytes. So when you need the new memory, all you need to do is find the suitable linked list and maybe pick the first one or maybe pick the best one. So it makes finding your available hole very, very fast. But again, as the best fit, merging is very, very slow. Merging is slow. What do I mean by merging? When a process dies, okay, you need to merge the neighbors of those processes in memory location together so that it makes a large whole. But that operation becomes large; it becomes a linear operation. Okay? So finding the whole is very fast, but merging is very very slow. I mean, it's older than slow. It's older than slow. Okay, any questions? So these are the algorithms that we use to find locations for our processes. And the problem with all of these algorithms is that, is that this is a process and this is a process and this is a process and this is a process. These algorithms think that the processes has to use a physical memory in a contiguous way. I mean, if this is my memory, then A has to live here, B has to live here, and C has to live here. So all the other space of A has to be contiguous, and this one has to be contiguous, and this one has to be contiguous. And this is causing problems because they have different sizes and this creates some fragmentation. Some people say that instead of using these contiguous address spaces, let's divide the memory into pages, pages. And each process should have a fixed number of some known number of pages, and the pages can be at different positions of the memory. That's called a paging technique, and we are going to look at it next, if there are no questions. Okay, so that was the fixed size. Those algorithms were for contiguous memory management. If we use some other type of technique, which is called the virtual memory or the paging, virtual memory uses this technique of paging, then we can do more. Then we can be more efficient. Okay. There is a need to run programs that are too large to fit in the memory. That's another reason. Let's say I have 32 kilobytes of memory, but my process needs 64 Ks of memory. So what do? Do I say, okay, I'm not running this? No, I can still run my program because I would load only the necessary parts into the memory, and the rest would stay on the disk. Whenever I need the other parts of the memory, I would load them from the disk. And this solution was available from the 1960s. They say that each programmer divides his or her program into pages or the overlays. Okay. So when I write my program, okay, this is my program. I would say that, okay, I have overlay 1, overlay 2, and overlay 3. Okay. I divide my program into 3. And I will say operating system that, okay, you can load these overlays, separately from each other, and my program will work. And so it is my responsibility to divide my program into 3 or 4 as a programmer, which makes it very difficult for the programmer to write programs. Because when you change your program, this has to be changed again. It has to be done very, very carefully. So instead of using this 1960s technique, there is another method, virtual memory. Each program has its own address space broken up into chunks called pages. Okay, so I divide operating system divides my program into a number of chunks called pages. Okay, the operating system does it automatically, and these pages, they don't have to stay on the memory all the time. Some of them might stay on the disk, and some of them will stay on the memory. And maybe just show this example first. This is my virtual memory. This is not the real memory. This is 64 Ks of size, okay? And my virtual memory, my virtual address space is divided into these virtual pages, okay? I have pages. These are pages. So my program can address any of these bytes from 0 to 64K, but my physical memory is small. My virtual memory is 64K, but my physical memory is 32K. So my physical memory will not fit into the my process memory will not fit into the physical memory. So what do? I divide my virtual space into fixed size pages. So I have total of how many? 16 pages here, okay? So the page number 0 is here. It says that this page number 0 lives at this memory location, the physical memory. Page number 1 is coincidence, it lives at the same position. Page number 2, it lives here, and it goes like that. And page number, let's say 1, 2, 0, 1, 2, 3, 4, 5, 6. Page number 6 does not have a position in the main memory. It is not loaded, it stays on the desk. Okay? For now, maybe I don't need it, okay? This page, and this page, they are not in the memory because I don't have enough space to have them in the memory. With this technique called paging, okay? With this technique called paging, I can have much larger programs than my physical memory allows, which is a very, very big advantage. The other advantage is that each program, each process would have its own pages, and as you see, these pages don't have to be in order. They can change their order. So it doesn't matter. It doesn't matter where my program is. It doesn't have to be contiguous. So memory allocation is much easier. We don't have this problem of fragmentation, memory fragmentation, because whenever I see a new available space, or whenever I see in my virtual memory, I can always assign some real physical memory address to any of my pages, just drawing an arrow or assigning a pointer. So I don't have this finding the best position for my process problem anymore. It is solved automatically. Okay, this is called paging. Let's go back and talk a little bit about it. Maybe this is a good picture to talk. This is my CPU. When my CPU says that I will access, I will do this. Move R register to, let's say, address number 30,000. Okay. Move this R register to address number 30,000. So this memory management unit, okay, memory management unit takes this value of 30,000 and it maps this value of 30,000 to the physical memory address because this is a virtual address. Okay, where is 30,000? 30,000 is somewhere, I guess, here, right? So it is here. So the memory management unit comes here and finds that the page for the 30,000 is not loaded. It is not in the memory. So what do? It it gets this page from the disk and it loads into the memory, let's say to this position, and it returns the address for that position, and that address is sent to the memory, and I load it. So there is a memory management unit that converts the virtual addresses to the real addresses or the physical addresses. Okay. So these virtual addresses is my process always uses the virtual addresses. Then my memory is using a different address space than my virtual memory. Memory management unit is responsible for that translation from the virtual address space to the real address space using this paging mechanism. Okay, if I go back a little bit, so with the virtual memory, we convert the virtual address, okay, to a physical address. The virtual address is used by the process, the physical address is used by the memory, and mapping is done by the pages, okay. The mapping process from the virtual address to the physical address is done by the pages, and groups of 4 kilobytes, groups of 4 kilobytes. It doesn't have the page size doesn't have to be 4 kilobytes, but 4 kilobytes is a very popular page size, okay. And the mapping need not refer to contiguous areas of physical memory. When you are doing the mapping, it doesn't do the mapping, okay. See, all these arrows are intersecting. This page goes here, and this page goes there, and it goes up there. It doesn't have to be contiguous, so I don't have that memory fragmentation problem as I had before.